Okay, now we're going to move to our module 9. And then this module 9, we're going to look into shift register. So what is the objective for you to learn shift register? First of all is for you to introduce the characteristic and function of shift register. And then second, to highlight different type of shift register. Third, to introduce shift register IC. And lastly, to explain shift register counter. So what you're going to look into this module 9 is on the basic shift register function. So on the shift register, you're going to see 4 different type, which is SISO, serial in, serial out, SIPO, serial in, parallel out, PSO, parallel in, serial out, PPO, parallel in, parallel out. And after that, you're going to look into a bidirectional shift registers. And then shift register counter, there is 2, which is ring counter and Johnson counter. So this one is just the overview on the contents under our module 9, the last module for your digital logic. So let's take a look first under our basic shift register function before you go into deeper. So shift register or SR is a register in which binary data can be stored. So this is the first key hint that you can also remember. This one can be also been asked in your part A for your final exam. And this data can be shifted to left or right. So either left or right when the signal is applied. So it consists of arrangements of FF. What is FF? So remember, right? FF is your flip-flop. So in your module, you can look into page number 33. I think it's wrong. Memory device in digital system. Maybe you can take a look under MS or pages 33. So digital system important in application involving the data storage and also data transfer movement. This one is under module page number 7. So on the flip-flop as the storage element. Last time you noticed that a flip-flop have a memory. So maybe it's capable also to be a storage. So over here you will be seen with the elements of flip-flop that can become as a storage. So over here you can see when A is 1, where's A? Okay, is 1 on the D. So Q become 1 at the trigger edge of clock, or remain A if it already. So this is the output, and also this is the input, and this is the output. So you can see this similarity of input and output for the flip-flop. Same also with another ones, which is if you have 0. So it's look like that your value number 1 is been stored, and of course it is similar also. You can see over here when 0 is on D, so Q become a 0 at the trigger edge of clock, or remain 0 if already. So you can see over here it will be 0. It will be 0 when the trigger clock. So if it is positive clock, a positive edge, it's going to be at a positive low to high, and if let's say negative, high to low. So depend on your clock also, but it will store first the value, then it will come out when it trigger the edge of the clock. So each flip-flop store 1 bit data. More bit required. If let's say you want 2 bits, then you need to have another flip-flop and so on. So the basic data transfer and movement in SR. So 4 bits are used for illustrations. The bit move in the directions of arrow. So if over here, this one is the one that I said Pico, CISO, and whatever. So serial in, shift right, serial out. So this one is under shift right. You can also have shift left over here. It is similar, which is shift in and also shift out. This one only the different and the vice versa on the direction. And then after that you have the parallel in, serial out. So you can see you have a parallel in, and then you can have the serial out, whether to you can see over here it's to your right, and you can also have the serial in, parallel out. You can have the parallel in and then parallel out directly, and you can also have like a rotate right and then rotate left, and there is also several. Let's check a look. This one, what is Pico, what is CISO, what is PISO, and so on. So this is how the movement can be. So a register can shift data 1 bit at one time only. So each time we're going to shift 1 bit, 1 bit, 1 bit, and 1 bit. The logical configuration of serial SR, a chain FF, which is flip-flop, connected in cascade. The operations of SR synchronized using common clock. So you're going to use a common clock. Shifting n bits SR will lose all data after 2 n clock cycles. So the solution is you need to use the rotations. So under CISO, you need to know all the characteristics under CISO, PISO, PIPO, and also SIPO. Accept data serial, 1 bit input at time on the single line. Each clock pulse will enter 1 bit. I think you can easily read it. This is the characteristic under CISO, and you can see over here you have the data in, and you have a data out over here, which is serial in and then serial out. If parallel, it's from up or bottom normally. Easy to understand. So here there is example. If let's say you have 4 bits of 1010, begin enter serially into the register. You can see that you give the value of 0 first, and then 1, and then 0, and then 1. Every clock cycle data is shifted to the right positions because it's stored first, and then later on it will be changed. For n bits CISO, it's required n clock cycles to completely entering the shift register for the first data entered to appear at the output. So if like this is going to be LSB shifted in first. So it's not giving you the examples of the output, but it's okay. Over here you have the example. If let's say first of all you have the value of 0, of course first you're going to pick this and then this and then this and then this from LSB to MSB, right? So first 0, and you're going to get the output 0 also. First over here, this is the 0 first, and then you can see it's moved 0 1 0 1. So first of all, you're going to see your 0 will be out first, and then after that 1, and then 0, and then another one is 1. So if let's say you have 4 bits, you need to have another extra clock, which is to fully finish the cycle. So you can see over here what is the output also 0 1 0 1 0. It can be continue. So this is also another example of seesaw. Please try to do all the example, and this one too. This one is try to test your understanding. So after you learn on seesaw, you need to move to SIPO. So you can see over here you have the data bits are enter seriously 1 bits at one time. So still similar, it's going to be serial in, and the output is different, which is output is parallel. You have the serial in. If let's say previous one is seesaw, it's going to be out like this, but because it SIPO, P is parallel, S is serial, so P is parallel, that's why it's going to come out like this. Is okay. So over here for seesaw, output only at Q3, but for SIPO, output is Q3 Q2 Q1 Q0. Because over here you can see how it's the connection look like. So you're going to see only at the end, so that's why you will get only Q3 at the end of your clock flip-flop. But for SIPO, because it will be parallel, each flip-flop you're going to come up with the output Q3, Q2, Q1, Q0. So show the state of 4-bit SIPO shift register for the following data input 0 1 1 0. So first of all, MSB shifted first, and clockwise the register initially all is 1. So first of all, you already have the initial states, which is O is 1. So you can see over here. So initial value of your F output is 1 1 1 1 1. Sometime normally in our previous example is low, right, or 0, but this one is high initials, so you can see like that. So after that you need to see what will happen, because this is the input and this is the clock, and what is basically happen using the flip-flop. Is it toggle or similar? Only at the positive edge clock over here. So it will be triggered like this. And the rest. So you can see how the timing diagram, I think timing diagram also I already touched a lot. I'll try to do this as exercise, and this is the example similar to this one also. Okay, let's move to, because this one is all example, I want you to do it by yourself and then ask me if you didn't understand. Because normally in class when I ask anyone who did not understand, so most of you said no. It's okay. Let's continue. Okay, after seesaw and seepo, you're going to have the input of parallel first. Previously, you look into serial input. Now you have the parallel input, but the output is serial. So that's why you will look like this. And you still use over here D flip-flop. There is a lot and shift, yeah. So this this is how it's look like inside the block. I think there is no much different. Only the different you need to know on how the inputs going in and how the input going how the output going out. Something like that. Another one is P-PO. P-PO is P is parallel input and then parallel out. It's not too complicated under all these serial register. Now let's take a look into shift register counter. So under a shift register with a serial output, you can see SR serial shift register have ring counter and also Johnson counter, isn't it? So you can see that in normal counter, to provide individual digits output instead of binary or BCD output, you're going to adding the decoder. But much simpler to be use a different counter structure with a simple decoder, which is shift register. So shift register counter, which is under ring counter, there is several, which is ring counter and also Johnson counter. So this one is under ring counter, a type of seesaw shift register, but final output feedback to the first input. So you're going to see it ring in like a looping. The ring counter use first one flip-flop for each state in its sequence. So if let's say you have 10 bit of ring counter, there is a unique output for each decimal digit. The one is always ring 10 goes round the ring at each clock pulse. So this is the example for your ring counter. You can see it will be looping back to the first flip-flop. So this is n bit, mode is modulus and state. So example, for a 10 ring counter, there are 10 flip-flop which made a mode 10 counter. So it will recycle after 10 clock cycles, isn't it? So please try to do this exercise example. You can check also in your module one by one. you can have take a look over here and with the answer. Then later on you can try it by yourself. And another one we're going to look into under shift register counter under Johnson counter. In Johnson counter, the last complement output is the feedback. So you can see complement output, not like this one, the last output, which is the Q bar itself, not Q bar, the Q itself, not the Q bar. So if let's say for the what is this Johnson counter, is going to be, where is it, last complement output. So example, if let's say you have the flip-flop, but can be implement with other type of flip-flop as well. This one is example to on the flip-flop only, but you also can apply another difference of type and the flip-flop. Number of unique states are 2 times the numbers of the bit flip-flop. So this is how it looks like. Johnson counter will produce a modulus of 2n, which is number of stage, and also modulus 10 aka mod 10. So here it is. This is the example, and you can try it, the different how it's going to look like. Basically you can see over here, this one of course it will be a ring because it's not a complement. You will normally use the Q bar. Q bar is under Johnson counter. So there is a summarization for ring counter, which is n bit equal to this one, you already know, and this is a truth table and also the state diagram. And this one is under Johnson counter, the different at this part and also in the data representations. So other characteristics of Johnson, always exist 2 unique bits compared to the other state. It will be only required to input decoder to decode a state. So this is an example. So under comparison, this one is just a theory. You need to know the comparison between all the shift register and also counter, which is under ring, Johnson, and also binary. So this one is only on the quiz like examples test only. So there is a solution and etc. So we already cover all under module 9. So I hope that you can go through it and ask me a question if you didn't understand. I'm not going to explain in detail because every time I give you video and I explain it, when I ask, there is no one asking me back anything like you already fully understand. But when it's come out to your test and quiz, it looks like you still didn't understand, right? So why don't you pick or search a question about which part that you didn't understand, something like that. Okay, I don't want to mumble around again, so thank you for watching and have a good day. Bye bye.